in Tufts. And so let me introduce myself a little bit, and then we'll get into today's session. Um, so most of the people who you'll find teaching at a place like Tufts are professors, and most of them in a department like computer science do research, which means they do studies and experiments to find new ways to do new things. And many of them spend their careers at universities like Tufts. I'm what's called a professor of the practice. I've been doing work with computers for, well, I'm pretty old, for over 50 years. So I started programming probably before your parents were born, which is wonderful for me because so many interesting, exciting things have happened and changed during the years that I've worked on this stuff. But in fact, my career was mainly working on building actual computer systems, sometimes doing research on them at companies like IBM and at Lotus. Um, Later in my career, for about 15 years, I was known for working with the people who built the World Wide Web. There's what's called a standards organization that brings together all the people and all the companies who are interested in making a system like the web work. And I had the great privilege of working with some of those people for about 9 years. Starting in about 2004, I was on the overall technical steering committee that tries to make sure that the web works, working with people like Tim Berners-Lee, who was the person who invented the web. I was talking to Ellie about that a little earlier. It was a super exciting experience for me. And about 12 years ago, I came to Tufts. I've always liked teaching. I did a little teaching at Stanford when I was a graduate student many years ago. And so for the last 12 years, I've had a great time here at Tufts teaching mostly undergraduate students, like most of you will be if you come to Tufts. I've taught our Introduction to Computer Science course several times, and also well known for teaching the course that this session is from, which is the course that you take if you decide you want to be a computer science major and you want to get really serious about not only being a better programmer, but learning how computers work. So that's what I do. One other thing I just wanted to share with you before we start. It turns out that before I went to Tufts, before I came to Tufts to teach, my son came here as an undergraduate. And so I had the experience you're going through, especially if there are parents on the call, of being a parent of someone who is applying to Tufts. And I have the perspective not only from the students I teach, but from my son and from his friends, many of whom I'm still close to. So what I wanted to invite you is there's no real way for me to talk to you on this Zoom session. But my email is up on the slides, and I'm really easy to find if you do a Google search. So if you have any questions about anything, if you're interested in what we discussed in this talk, but if you just want to find someone who can point you in the right direction about Tufts or computer science at Tufts or what it's like to apply or anything like that, feel free to drop me an email. I'm always glad to hear from you. So what's this session that we're doing today? So let me start by asking you two questions. And I think Ellie tells me that the way we've got this Zoom session set up, if I ask you a question, you can type your answers into the Q&A box that I think you have, I hope. So I'm going to invite you to do that. Usually when I gave this talk in the past, it was live and in person, so I got to ask people questions. And if I were doing this in our actual class, I'd be asking questions. So let me point out one other thing. The class this comes from is a pretty advanced class. But this particular session, you don't have to know anything about computers to understand. And it's actually about some of the things that make computers really interesting systems. So don't worry if you haven't studied computers, if you're not sure if you're interested in computers, this should still be fun. Let me ask you two questions. The first is, even though you're not experts, a lot of people have sort of heard that there are bits in computers. So if you think you know anything about what a bit is, if you could just type into the Q&A box and say, I think a bit is this, or this is what I know about bits. It'd be interesting to see what you think kind of going in. So I'm gonna wait just a second while people type. All right. So I don't think you can all see these. So let me read some as they're coming in. Somebody wrote, and I'm going to not give your names, so you're comfortable. There are no dumb entries or answers or anything. Someone said a small unit of data in memory. That's going to turn out to be right. The classic answer someone gave is they can be zeros or ones. So I want to talk about that in just a minute. Several people have said a sequence of 8 ones and zeros. So let's be sure to come back to that because that's close. Smallest unit of data a computer can store and hold in binary, smallest unit of data. Okay, all good. So, and if you don't know anything about it, it's fine. That's what you're going to learn today. But let me just zero in because one of the classic answers you get is there's zeros and ones. And you're going to find out that's kind of true. But let me ask you this, and you don't have to answer, just think about this. If we took a real microscope to a computer chip and we could really zoom in and zoom in and zoom in because somebody's told us there are millions and billions of these bits in there, do you think we'd see little zeros and ones? So that's a really interesting question. So keep that one in mind because you're going to find out that zeros and ones is kind of right, but it's going to be trickier than that because no, you don't really see little ones and zeros when you look in there. So let's think about that. The other question I want you to think about, and I'm not sure it's worth having you type, but just think about this for a second. These days we have computers. I'm looking for my cell phone here. We have computers like this, and they fit in our pockets, and they can do all kinds of things. We take pictures with them. We listen to music on them. We send emails with them. We send text messages. If you had gone to someone 50 years ago and not even talked about computers, you had just said, I got this machine and it's the same machine and I can use it to keep my business accounts. I can add up numbers. But I can also use it not only to sort of look at photographs, I can edit the photographs. I can make the colors better. I can make the pictures sharper. And then in 5 minutes, I can switch and I can use it to play music. People would have gone, that's completely crazy. How can you have one machine do all that stuff? I mean, this is 50 years ago. A while ago, someone invented the phonograph and it can play music. And that was kind of something. And people invented cameras and they can take pictures and that's pretty good. And we got adding machines and you can type numbers into them and add them up. And that was sort of something. But I have no idea what kind of machine you have that it's really the same machine and it knows about music and it knows about pictures. That's really weird. What kind of machine is that? And it turns out that that's one of the things that makes computers such an incredible change in our society and such incredible things to work with, whether you're a computer specialist or not. And it turns out that if we go exploring what we're going to do today for the next half hour, which is to look at what are these bit things, we're going to find out sort of the magic that makes all that possible, that makes it possible for us to build just one machine that does all these things. So to do that, we're going to take a little detour and ask ourselves a question: what is information? And while we're doing that, we're indeed going to explore what is a bit. And based on that, we're going to dive into what I was just talking about, which is how did we build these incredible machines that do all these things, including, by the way, making possible the web conference we're having right now and having you look at these graphical slides that I'm showing and hear my voice, and it's all going through your laptop or your telephone or your computer. So let's dive into some of the interesting history here. And I'm going to show you the picture of this man, who is one of the people most famous for contributing to the theory of computing and information. And his name was Claude Shannon. He did a lot of his work in the 1940s, which is around the time just after the World War, or during the Second World War, when people were building the very, very first electronic computers. They were very big, they filled rooms, but in fact, because the engineering was very primitive, the amount of information they could store was tiny compared to what we do today. And we'll talk about that in a minute. Shannon was a very interesting guy. He actually worked for the phone company. And at the time, there was only one phone company that connected all the phones in the United States, and they owned all the wires, and they would rent you a telephone, and you could, of course, use it to dial other telephones, talk to people. And the phone company went to Mr. Shannon and they said, you know, we have this idea that we could use these wires for more than talking. We could send other stuff through these wires, but we don't really know how to think about that. We don't know what we could send through the wires. And we need to know before we put a lot of money into this, is this going to work? So you're a very smart guy. He had already, when he was a graduate student, a master's student, published some very interesting papers on computing. So he started thinking about this and he said, you know, I think we got to ask ourselves, maybe we could do this, but we got to figure out how much of this stuff we could send through a wire. And frankly, I don't even know how to talk about how much information we have. I mean, if you give me something like a brick, I can hold it and go, that's pretty heavy. It's pretty massive. There's a lot of stuff here. And if you give me a feather, I kind of go, well, this feels lighter. There's less mass. And I can look at the room I'm in and I can go, yeah, it's pretty tall. It's bigger than this. But if you said, well, how much information can I send through that phone wire? He goes, I don't even know how we think about that. I mean, how do you measure it? You can't weigh it. Can we distinguish more information from less? And he started thinking about this and thinking about it. And he came up with this amazing way of looking at it that has changed the way we think about it ever since, and that is underneath everything we do with computing. And he asked, what kind of units? I mean, when I measure the room, I can say, well, it's that many feet tall. And if I see how much things weigh, I can say it's that many pounds. How do I measure how much information we have? And he came up with this wild idea. Well, first of all, he said, but it's not like it's all the same. If I go to, like, some of you may know about this, that the United States government has a very, very big library where for years they tried to keep every book that was ever published. And you go, well, that feels like a lot. It seems like a lot more than one word, but I still don't know how to measure this stuff. So he came up with this idea that what's really interesting is what happens when I try to send you the information that's in a book. I want to send you the words. I want to send you an email, but also sometimes I want to send you a picture or a sound recording. So he came up with this idea, and this won't be obvious right away, but I'm going to explain it to you. Often when I talk to you, I'm answering questions. And the way Shannon did it is he said, we're going to agree in advance on what the questions are. And we're going to agree on the ways I can signal whether my answer is yes or no to your question. And then when I send you the signal, you'll know my answer. So here's an example. You and I are going to decide whether we want to have dinner together. But I'm trying to give you my answer as quickly and simply as possible. So I don't want to say a lot of words. We're going to agree in advance. I'm going to send you one signal. And if I say yes, we've agreed in advance. We're talking about dinner. So if I say yes, that means we're going to dinner. And if I say no, it doesn't. So I hope that makes sense. Now, I chose yes and no. But let's say we wanted to play the same game and we couldn't hear each other, but you could see me. I could say, look, I'm going to hold up a piece of paper. I'm going to hold up a yellow piece of paper if the answer is no, and I'm going to hold up a purple piece of paper if the answer is yes. When I do this in class, I sometimes actually bring some pieces of paper in. So that's very different than yes and no, but I hope you can see that with those two pieces of paper, I could signal the answer to you. Purple for we're going to dinner, yellow for no. I could take a flashlight and I could say, if I blink the light once, that means yes, I'm going. And if I blink the light twice, it means no. So we've done some interesting things. We've decided that we're going to think about questions that have only two answers. I'm going to dinner. I'm not going to dinner. We've noticed that once we've agreed that that's the question, I just have to send you a signal that goes two ways. It could be thumbs up and thumbs down. It could be a purple piece of paper or another piece of paper. It could be a flashlight. All I got to do is convince you that you know the answer to my question because we've agreed in advance what the signals mean. I need to tell you which of two choices I'm making, and we can do that in any way we've agreed on. There's a typo on the slide. It should say, I'll fix that right now. That's what I would do if I were teaching in class. There you go. I make mistakes all the time. I just made another one. Good. So I could wave flags. I could use traffic lights, two lights, green, I'm going, red, I'm not. I could send you an electrical signal. That sounds like computers a little bit. So here's the idea. Whenever two parties communicate, we can view the communication as answering one or more questions. We agree in advance on the questions. Maybe we're talking about going to dinner, maybe something else. We agree in advance on how I'm going to signal you. Green light, I'm going. Now, what if we have more questions to answer? What if we're thinking of going not only to dinner, but to a concert as well? So maybe we're going to have dinner and go to the concert. Maybe we're only going to have dinner. Maybe we're only going to go to the concert. Maybe we're not going to go to either. Question.
Do you want to reshare the slides?
Yeah, I just got the signal that sharing had stopped. Zoom, I guess, decided. But you've been hearing my voice all along. Okay, so you haven't missed anything big. Let me go find the share screen button. There it is. Share screen options. Nope. Sorry about that. I think when I did that editing, it decided that was a different window. Share. Got it back?
Yep. It's
okay.
Perfect.
So all you missed was me showing this last thing on the slide that says we're talking about both concert and a dinner. So here's the question. If I say you still only got one flag, one green or red light, can you answer both questions? And the answer is no, you can't. If there are only two choices, then I just have to say yes or no. But we've got four possibilities here. Not going anywhere, going only to dinner, that's second choice. Going only to the concert, third choice. We're going to both. That's four choices. And it turns out that to do that, I'm going to have to signal you twice. I'm going to have to answer two questions. Are we going to dinner, or are we going to the concert, or are we going to both? So yes, communication is answering questions. It's choosing among possibilities. Just saying yes or no isn't enough. We have to agree what the choices are. If I just come up to you and I go, hi, Bob, yes, you're going to go, yes, what? But if I say, when I come up to you, I'm going to tell you whether I'm going to dinner, and then I walk up to you and I go, yes, you'll know what I mean. And if I say, when I walk up to you, I'm going to answer two questions, whether I'm going to dinner and whether I'm going to a concert. And I go, no, yes, then you'll know what I'm going to do. because we've agreed in advance. And here's the key point. The more choices we have to make, the more yes, no answers we'll have to communicate. So to handle both concerts and dinner, I had to answer 2 questions. And we define the ability to answer a single yes, no question as a bit. That's what 1 bit of information means. It's something that can go 2 ways. And if we agreed that this one means I'm not going to dinner, and that one means I am going to dinner, or whatever the choice is, I've given you 1 bit of information. And we define the amount of information as the number of yes, no questions to be answered. So in Shannon's theory, if I have to answer about dinner and the concert, then that's 2 bits of information because I had to give you 2 choices, each yes or no. And you know what? That's, that handles, you're going to find out that handles a lot of interesting stuff. But it's not everything we want to communicate. If I want to just tell you how much I love you, yeses and nos probably aren't the right way to do it. And indeed, computers aren't very good at that stuff. But sort of factual information, clear choices, that's what computers are good at. And this is why, because they do store bits. The term bit actually comes from Shannon's paper, the one he wrote with this theory, which is linked on the slides. And he got the idea from a friend who worked down the hall from him. So here's an interesting question. We said that computers can do music. So Beethoven's Ninth Symphony is a famous piece of music. Wonder how many bits I need to use to send you Beethoven's Ninth Symphony. We'll think about that in a minute. Well, it turns out to be a trick question because I told you that information was about making choices. And you need to ask yourself, well, what are the choices here? Are the choices clear? And that's why this is a trick question. What if I go, aha, we've agreed in advance that we're really only thinking about 2 works of music. I've got this CD here that's got Beethoven's Ninth Symphony on it. And I've got this one here by Squirrel Flower, who's one of the cool new singers out there. And all I need to tell you is which one I have in mind. Well, if we've made that agreement in advance, haha, I only have to send you 1 bit. But usually when we say, can I send you this music, we mean something like a recording. Well, what are our choices then? Well, the answer turns out to be, let's consider a CD like this. It runs for about 70 minutes, according to the standard, if you fill it up. We have to send you enough bits to choose among all the possible stereo sound waves that we could record for 70 minutes. And at each point, that could have any sound, a sound wave that's small, very quiet, or very high frequency because it's a flute, or very low frequency because it's a bass guitar, which I play. So there are a lot of choices every moment in time for 70 minutes. And the bits we record essentially are choosing among all the possible sound recordings. And an interesting little fact is that I mentioned Beethoven's Ninth Symphony because when they invented these compact discs that look like this, which used to be very, my camera looks like it's not focusing, but it's a compact disc. When they invented the format, the people who sold records were very interested in classical music. And they said, we really want to be able to fit a good recording of Beethoven's Ninth Symphony on one of these. And it runs just over 70 minutes. And they said, it turns out that to get a good sound recording wave, you've got to sample at about double the frequency that the human ear can hear, which is about 20,000 times a second. So they went for a little over 40,000 times a second. And it turns out that the number of bits you can store on a compact disc is just under 6 billion, which is just about long enough to hold Beethoven's Ninth Symphony. So there are 6 billion yes/no questions answered on a full compact disc. What's the sound here? What's the sound here? What's the sound here? What's the sound here? And in a moment, you'll find out that we do that by recording numbers on the disc that indicate how high the waveform is, and we're about to explore that. I'll also point out, because this all sounds pretty new and high tech, that it turns out, I found out some years ago, that Shannon in the 1940s wasn't the first person at all to have this idea. The oldest one I've been able to find is this piece of writing. If you look at it, you may notice that the writing sounds a little old-fashioned. That's because this was written in the 17th century, the same era that Shakespeare wrote, well before the American Revolution, by Sir Francis Bacon. And you don't need to understand all of this, but where he says you can encode the alphabet resolved into transposition of 2 letters only, he's got that same idea of yes/no choices. And you're going to find out how we do that with words today in a minute. And he points out here that once we've done that, we can do exactly what I just told you about when I answer questions. I can signify the intentions of my mind at any distance by sending you this signal of 2 letters only, yes, no, YN, whatever. So it's very interesting that Sir Francis Bacon, who is a very interesting scientist, some people thought he wrote some of the plays attributed to Shakespeare, actually had this idea roughly 300 years before Shannon. So what have we learned so far? Bits encode yes/no choices. To communicate, we need to agree in advance on which bit patterns represent which choices. More information means more choices, which means more bits. Now let's talk about computers. I hope it starts to seem reasonable that if instead of using flags or words, I could find a way to put into a computer hardware device something that could be in 2 different conditions, 2 different states, that I could use it to record the answers to any questions I want. And that's exactly what we're going to do. And it's going to turn out to be the reason that we can work with so many different kinds of information. Because the only thing this hardware needs to know how to do is be in 2 different conditions. And if we agree that this condition means I'm going to dinner and this condition means I'm not, then we can use a computer memory to remember whether I'm going to dinner. And if we agree that it's going to mean any other choice we care about, that same bit, that same piece of hardware can be used to remember the answer to that question. So we can store any information in a computer memory as long as we can agree on which bit patterns represent which choice. And you're about to see, I haven't proven it yet, why computers can use the same hardware to store so many different kinds of information. So we got 2 things we got to answer. One is, so how do you actually build these computers that got these bits in them? Which I'm going to look at first. And then I've got to circle back because I haven't really showed you how we put words into computers, how we put pictures into computers, how we put numbers into computers. And that's what I'm going to do right after I show you some of the sort of hardware choices we have. This happens to be a picture of one of the very, very, very earliest computers. It was built in the 1940s, right after the war. There's sort of an interesting reason I chose this particular early computer. It was the first one you could buy. It was the first one that wasn't someone's lab experiment. You could go to the Ferranti company, give them money, and they would actually sell you one of these. Not exactly an iPhone, but you could buy one for several $100,000. One of the reasons I quite like this one is that 2 of the people who programmed it and helped to design it were named Mary Lee Woods and Conway Berners-Lee. And it turns out that 45 years later, their son, Tim Berners-Lee, created the World Wide Web. And as I mentioned a little earlier, one of the things that was most exciting in my career was working with Tim, which I did for over 10 years on these technical committees that were responsible for various web technologies. So that was really fascinating to see what went into building the web and how Tim and many of the experts who worked with him went about it, what they thought about. But it was also kind of fun to find out that his parents, whom I never met, but whom he talked about a lot, met working on this particular computer. So that's kind of fun. And it also allows me to point out that the very early computers used devices like the ones in the middle here, what we in the United States call vacuum tubes. A tube like this might have been able to store 1 or 2 bits. Sometimes you needed 2 tubes to store a bit. So you were not going to put millions or billions of these into a computer. You'd be lucky to put 1,000 of them into a computer. So the early computers did not work with many bits at all. Think a few thousand at most. And in fact, I don't have a picture of it here, but this computer also used something like a very old TV screen with glowing dots on it to hold about 1,000 bits at a time. Very expensive way to do it. There were mechanical things. Some of you may know what a relay is. Turns out this is an electromagnet, and when you run a current through it, it can make the flapper on top go up or down. So you could say, down, I'm going to dinner. Up, I'm not. Well, if you can find a way to wire this up, which you can, so that when you pull it down, it stays down, then it will remember that I'm going to dinner. And there were very early computers. There was one at Harvard that was very famous that was built all out of these things. And when this computer ran, it would go clatter, 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 because you'd feel all these little flappers would be going up and down. Yes, no, as it did the computation. So one of the big advances that we've done over the years is we got to make these things smaller. And we've also got to find a way where we don't have to leave them in the computer. I want to be able to, these days, look at on the bottom, we've got USB keys. I want to put that in my pocket. I want to take it on a trip with me. Well, you're not doing that with vacuum tubes. So one of the early ways we did that, this is actually something that I prepared. I don't know if I get my camera to focus on this. You should be seeing a card with holes in it. If there's a hole, that's a 1. If there's no hole, that's a 0. That's a punch card. And this is a program that I wrote when I was a freshman in college at MIT in 1970. We didn't have hard disks yet then. We didn't have USB keys then. There were memories built out of little magnetic donuts. There were memories built out of little transistors and eventually on chips like you see in the integrated circuits. But the bits, the same idea. In the early days, a bit took a lot of space. Then we learned how to make them a little smaller with magnetic core memory donuts. Then we learned how to squeeze millions of them into integrated circuits and billions of them, which is what we do today. And we learned to make ones like the one in the USB key that don't lose their bits when you pull them out of the power supply. You can put them in your pocket and they remember their bits, but they're all yeses and nos, things that can remember 2 choices. So I hope that part makes sense. Now, if I asked somebody 50 years ago, what do computers do? They'd probably say, well, they do numbers. They can add numbers. They can subtract them. They can average them. They do stuff like that. And so far, all I've told you is, well, we got these bits, and each bit can go 2 ways. So I haven't really told you how to put a number in a computer. So let's look at that. What if we want to encode numbers, which we do all the time? And this is getting closer and closer to what you're going to learn if you take a programming course. Maybe you're taking in high school or at Tufts if you come here. Well, remember, I told you it's always about choices. We had to agree whether we're having dinner or not. We had to agree which sound wave we wanted. Now I'm going to have to figure out which number of all the numbers I could be storing, which one do I want to remember? Which one do I want to send to you? So remember when we were talking about dinner, I said, well, the purple flag I'm going to label as I'm going to dinner, and the yellow flag is going to be I'm not going to dinner. What do I label the flags if I want to encode numbers? So here's how we do this. Let's say, and you'll see later why I chose this example. Let's say I want to figure out how to put into the computer one of these 8 numbers. And if you notice, there are 8 of them: 1, 2, 3, 4, 5, 6, 7, 8, because there's a 0 there as well. Now I've got to choose among 8 things. So if you think about the flags or the signals, one flag was good enough to make a single two-way choice. I could choose between 2 things. When we had dinner and the concert, 2 flags was enough to make a 4-way choice. No, no, yes, no, no, yes, yes, yes. It turns out that each time we add a flag, a bit, we double the number of choices. Because if you think about it, let's say I have 2 bits. There are 4 different ways they can go. No, no, yes, no, no, yes, yes, yes. 4 choices. Well, if I add another bit, that one can be either on or off, no or yes. So if it's off, the other 2 bits give me 4 choices. But now if it's on, the other 2 bits give me 4 choices. So now I'm up to 8. So that's why I need 3 bits to make 8 choices. And I can make up any labels I want. Nothing says that no, no, no will be 0, or that no, no, yes will be 1. All I need to do is make sure I don't duplicate any. Because if I use the same pattern here for 2 different numbers, you'd go, well, no, yes, no. Does that mean this one or this one? You used it for both. And I go, well, I'm not going to do that. I'm always going to choose different. The pattern's always going to be unique. You're going to find out in just a moment that this pattern is not arbitrary. I chose it for a reason. And it is the pattern that almost every computer uses. Let me show you why. It doesn't really matter what I call these things on the left. I just have to be able to tell up from down, yes from no. So I could have also labeled these false and true. Any 2 labels will do if I can tell them apart. I'm going to tell you that if I just call the bit values 0 and 1, which is what some of you were talking about when we started, something very interesting happens. And that's why we do it. And let me show you what that interesting thing is. To do that, I need to give you a little tutorial. I bet a few of you out there know about binary numbering, and a bunch of you probably don't. And when we teach this at Tufts, a lot of students did know about it, but they kind of forgot and they're sort of rusty. So we remind them. Here's an ordinary number, the kind you work with all the time. 1, 2, 3. 123. Why do we write it this way? It's because there's a ones place, a tens place, and a hundreds place. So that means 100 plus 20 plus 3, right? So we got 1 of the hundreds, 2 of the tens, 3 of the ones, and so that's 123. What about these decimal numbers? Well, it turns out, I'm sorry, what about binary numbers? Well, the first thing is, it turns out that binary numbers only use 2 digits. You never see a 3. You never see a 2. You see a 0 and a 1. How does that work? Well, we have a ones place, just like we always did. But now instead of a tens place, we have a twos place, and a fours place, and an eights place. If you look over at the decimals, each time you went left, it was times 10. 1 times 10, 10 times 10. We have a thousands place. In binary, it's times 2. Times 2, a twos place. Times 2, a fours place. Times 2, an eights place. Okay, I'm a little confused. Show me what number we got here. Well, it's the same idea. This is the eights place, so I got 1 8. This is the fours place, but there's a 0 here, so I got no 4s. The twos place, I got a two. Ones, I got a one. Add them up, just like we did on the left. And that's the decimal number 11. It may not be obvious, but you can write any number you want using this system. You'll tend to have more digits because each of these digits can make 10 choices, and these digits make a two-way choice, which should sound familiar. Do I have a 1? Do I have a 2? Do I have a 4? Do I have an 8? And now you can see that the encoding, the labels I chose, which in some ways are arbitrary, for the bits that I'm going to use for these 8 numbers are the binary representation. So that's why we call the bits in computers zeros and ones, because it turns out that when we do everything we know about binary numbers, and I don't know if you know a lot about them, but mathematicians work with them a lot. And if you're a computer scientist, you'll start to work with them a lot. There's a lot we know, and we can apply that immediately. But you should get the idea that by having these bits in the computer memory, we can tell the computer which number we've chosen. And it should be pretty obvious that to go to higher numbers, we add more bits. So let's look at another example. The 4's place, the 2's place, the 1's place. There's a 1. There's no 0, there's no 2, and there's there's a 1, there's a 4, and no 2's, and that's 5. What's more is our computers don't just store these. They have circuits where you can say, I got a number here, and I got a number here. Would you add those up? And it knows how to create the bit pattern for the sum. So that's how computers do arithmetic. We've already done this, and I don't want to take too much time, so I'm going to actually skip this part and go on to something that I think you'll think is interesting. So I've kind of showed you how to store numbers in the computer. A lot of what we do is to store words. We send emails, we write documents, we do our homework. How do we use those same bits to store words? Well, it turns out, I know this sounds a little fancy, but these are the technical names. We decide that we're going to use numbers to represent each letter. So for example, here is Shannon's name, capital S, lower h, A-N-N-O-N. What if we assign a number to each letter? So seems like we've assigned 97 to A. Shouldn't be surprising. We got 2 N's here. That's the same number. Oh, there's another N here on the right. That's the same number. Now you're going to look at these and go, why 97? And the answer has to do with the history of how people did computing and punched punch cards and things like that. It doesn't matter. All you need to know is that everybody in the world has agreed on which number is which letter. And ASCII was the original standard for the sort of small alphabet that we use in the United States. And Unicode includes all the characters that are used to write Chinese, hiragana, Japanese, things like that. And it goes into thousands and thousands of letters, and it has to use bigger numbers to do that. So more bits. But look what we just did. I spent a few minutes telling you how computers could store numbers. I now said, hey, if we agree on which numbers represent which letters, I can use the same hardware, the same computer memory to store words and letters. And that's exactly what we do. We store those bits in the memory. And the computer mostly doesn't know if we think they're letters or not. It just knows bits. Very occasionally, when we're actually ready to print them, put them on a screen, that's when we go, oh, I think we're using these for letters. I need to print that letter. What's the mapping? Oh, 97 is an A. I'll print an A. But most of the computer hardware does not know whether we're working on numbers or letters. And that's how it's done. Now, there's something interesting going on. Look at the N and the O, 110 and 111. When I do my ABCs, LMNOP, O comes right after N, and it looks like we chose one bigger number. Looks like we're doing the letters in order. Hey, guess what? I can use the same hardware that I use to compare and sort numbers to compare and sort letters and get them in alphabetical order. That's exactly what we do. If you ask a computer to sort the words in your Microsoft Word file, that's what it's doing. It's representing them as numbers that are in the same order you want them to be in, and then it's sorting those numbers. At least that's the usual way it's done. So let's stop. We're going to take a minute to look at pictures, but I want you to see what we've done. We started with something that sounded pretty kind of vague. How do we measure information? What is information? Who's thinking about this? What are you talking about? And we went down this funny little path that Shannon suggested about making choices in bits. And it seemed to work pretty well. And we realized we can build computers that actually have hardware, real stuff that can store these bits and manipulate them. And suddenly we realized that we could use the same hardware, the same bit store to represent numbers, to represent letters, to manipulate the numbers, to add them up, to manipulate the letters, to put them in order. The same machine. And you can start to see where this is headed. I see a hand raised. Why do integer? I saw one person raise a hand, and I think I see a different person asking the question. So I'm going to answer the question that I see written, which is why do integers use 8 bits per bytes instead of 5 or 10? That is a great question. Some people may not realize if you haven't studied computers, most of them have what are called 8-bit bytes. It turns out that in almost every computer, it's actually pretty clumsy to go find a single bit. They're usually stored in groups of 8 that we call bytes, B-Y-T-E. It turns out there were computers that had a 5 and 6-bit bytes. And that stored letters that way. Back in the days, for example, there were early computers didn't bother with upper and lowercase letters. Too many choices and the memory was expensive. And it turns out the earliest letter codes were 5 bits and the earliest paper tape codes were 5 bits. For reasons that will become clear if you take a more advanced computer course, computers have a really easy time working with numbers that are powers of 2. 2, 4, 8, 16, 32, 64. See, I know what they all are because I work with them a lot. And 8 is a power of 2. So it turns out that 8 turns out to be a number. If you have 8 bits, turns out that's enough for 256 choices. And that turns out to be a power of 2, which is convenient. And it's big enough to store all the letters and most of the symbols like percent signs and parentheses. So that's the answer to your question. How are these integer values defined? How do these end up being the most efficient way to operate a computer? Some of the choices made for the numbers, for the letters, if that's what you're asking, are a little arbitrary, except that they're in order. Some of it's just history. It does turn out that for hardware reasons, it's quite easy to build circuits that are kind of yes, no, up, down, on, off. And it's often harder to build circuits that are like on a little bit, on a little bit more, on a little bit more. And that's kind of the best short answer I can give you because time is going to run out here about why this is an efficient way to build computers. But it turns out that most people have decided that sort of 2-value bits are the way to do it. We're going to have to wrap up in 3 or 4 minutes. So I think one of the things that's fun in wrapping up, we've looked at numbers, we've looked at letters. Pictures are a lot of fun, and we use our computers for pictures a lot. So here happens to be a black and white image of the Olympics logo. Think about Is there some way we could use that same memory, the same one that's storing numbers, same one that's storing letters, to store this picture? Well, turns out there are lots of ways to do it. But one way to do it is to look at each point on the screen and go, I don't know if you can see my mouse. Is that white or black? Yes or no? White or black? Two-way choice. Ooh, we've made two-way choices before. We know how to do that. Each one needs a bit. White or black? White or black? White or black? White or black? See if I can get this thing to show me pointer options. White or black, white or black, black. Oh, yes, 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 yes. No, 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 no. Yes, 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 yes. No, no, no. I don't know if you can see my pointer. So what if I fill my memory with ones and zeros? And whenever the screen is, I don't know, doesn't matter as long as we agree what each choice means, just like with the flag. If I agree 0 is white, and I agree with whoever built the display hardware that 0 means white and 1 means black, then these bits encode the Olympics logo. And there are many picture file formats that work exactly this way. There are others that are more efficient. There are others that go, look, I don't want to write however many this is, 20 zeros in a row. I'll just say, here come 20 zeros, or here come 80 zeros, or whatever we have in the bottom row. I'm not going to write them all out. So there are ways to encode this that are more compact. But once you unravel it, almost every computer ultimately gets a bit pattern like this. 0 for white, 1 for black, or we could agree the flags are the other way around. Maybe it's 0 for white, 0 for black, and 1 for white. Well, then I would turn my bitmap around. Each bit answers the question, is the spot black or white? I could do the same thing with the Tufts logo. Each bit answers the question, is the spot black or white? We've just seen how the same computer hardware bits can store pictures, words, and numbers. And if each spot is not just white or black, but maybe it's different colors, different brightness, well, we need more bits to say how much blue, how much red, how much green in each pixel. And that's exactly what we do. You can start to see how the same computer would let you edit the picture. Let me make it bluer. I'll multiply those blue values by a little bit. That's the kind of game we play. I'm going to skip compressions because we are out of time. You will find, now this is going to only be familiar to people who've written some computer programs. We store things like bank statements, student identifications, and stuff like that. Students don't live in computers. Bank statements don't live in computers. But we can build computer structures. And again, this is only for the people who've written some computer code. You'll understand that this is declaring variables that represent those things. We've learned how to store strings, names, characters in a computer. So maybe for each student, I have their name stored in the way we did Shannon, and I have their age stored in the way we did numbers. Now maybe I make what computer programmers call an array of 3 students. Mary, who's 15, Bob, who's 9, Tina, who's 12. Can you start to see, even if you're not a programmer, how something like this could work? How you could build a computer system that manages information about students and their ages and their student IDs and which courses they've signed up for, and how you could write some kind of code, I haven't told you how to do it, that could go looking to see if we have a student named Bob or a student who's more than 9 years old. That's what we do when we write computer programs. So I'm going to wrap up. I hope you've seen how we use this trick, if you will, to build machines that do all this stuff. We use bits to encode two-way choices. We can represent information in the bits. In other words, I'm going to tell you this bit means I'm going to dinner, or this bit means I want a black mark on the screen. I'm representing that information in the bits. We can then interpret the bit values properly. Oh, You've got a 0 there. That means you want a black spot on the screen. Oh, you've got bits that represent the number 66. Oh, maybe that's supposed to be a letter. I can interpret it as a C. If we call the state 0 and 1, then we can use everything we know about binary numbers to do arithmetic comparisons and so on. And we know how to build machines that do this and how to compute with those numbers, how to change them, compare them, and so on. So to wrap up, Shannon's information theory has had a huge impact. It's one of the great intellectual achievements of the last 100 years, and it's the basis for how we have built these machines that do so many amazing things. So thank you so much for coming, and thank you for your time. And as I told you, I'm going to go put up the first slide, and I will reshare again because it has my email on it. And if you want to contact me, that is how you do it.
Great. Thanks, everybody. Thank you, Professor Mendelsohn, for this class. Again, if you have any questions for Professor Mendelsohn, he's got his email up. You're also welcome to reach out to the admissions office on any admissions or other general questions about Tufts. And definitely check out those other Fall for Tufts mock classes and events that are happening for the rest of the month. Alrighty. Thanks, everybody. Okay.
I will stay for a minute and answer some of the questions in the chat, and you can ask me about bits and computers, or you can ask me about CS at Tufts or anything you like, or even just applying. I mean, I'm not an admissions expert, but I do have a son who went here a while ago, and I'll be happy to talk about that too. By the way, if I type answers here, can everybody see them or only the person who asked the
Yeah,
question?
if you type the answer, it should publish to everybody.
Okay. So everybody's seeing everybody's question and answer. Okay.
Yep, it
Because
should
I'm getting a lot of thank yous, and I'm very grateful for that. But I think I'm not going to answer each one individually. Do you know if Tufts works with CS? Someone's asking, do you know if Tufts works with CSS in biomedical engineering? Could you clarify which? I know some things on the web that are called CSS. Are you talking about computer science? I think. Yes. Okay. So I'm okay. Now I'm guessing. I'm going to assume that question is about does Tufts work with our, yes, we have, among other things, at least one, and I think several professors in the computer science department whose whole specialty is working on biomedical, a variety of life sciences related things. We also have a lot of cross-disciplinary things that involve students who are, for example, dual majoring in biomedical devices or engineering and computer science. There is a lot of cross-departmental stuff, both with life science, a more, I don't know if I should call this abstract life sciences thing. By the way, people are hearing me talk still. Is that right? If they're on, I hope.
Yep.
Yeah. So there are people who are working on things like protein folding and stuff like that. And yes, there have been people over the years, I don't know what's happening this year, working on things like biomedical devices, engineering, medicine pumps and things like that. But it's not my area of expertise. If you want to find out about that, you can contact the CS department. If you don't know whom to contact, you can send me an email and I'll find out who should get it and pass it on. Any other questions? How is researching at Tufts, in my opinion? That's a pretty broad question, so let me try to give you some useful answers. And it also depends a little bit, and you're welcome to type in clarifications if you want about what your question is. So if we just get that question from anybody, um, they're often asking, like, how's your graduate program? What is it like to do a PhD here? You folks are about to apply to our undergraduate program, maybe. So I'm going to give you an answer that's a little related to that. So, first of all, we are a research university. What does that mean? It means that particularly in the sciences and in engineering, but also in some of our other departments, we have a lot of professors whose main goal is to explore new things that no one's ever done before. That's what we mean by research. They do new theories, they do experiments to see what works. That is certainly true in computer science among other departments, but it's also true of many other departments. So I don't know if you're asking just about computer science. Um, we encourage our undergraduates to join in doing that research if they want to. And many undergraduates do, but certainly not everyone does. And what that means, well, it depends, but usually to do research as an undergraduate, you find some time either during the term if you're getting the requirements done, or over the summer potentially, to find a professor who's doing research and who will bring in undergraduates to partner with them and to partner with their graduate students. Some of those students get to publish papers with their advisors. Some of those students get to go to research conferences. Some of them just work on interesting things for a while. Um, some students write a thesis, um, as sort of an honors activity when they graduate, but it's certainly not required, and most students in computer science do not um, for their bachelor's or master's. I hope that answers, but if you have more questions about that, just ask. How is the student-professor relationship? Um, I think it's one of the things that Tufts is particularly well known for. And I can mainly talk for the computer science department where I work. Um, from what I've seen, it's unusually close. It's unusually informal. When I got here, I was stunned at how well many of even the senior research faculty knew a lot of the individual students. There are students in and out of our offices all the time. We consider some of them to be our friends. We invite them to stop by and chat about anything they want. A lot of the close relationships, I mean, first of all, if someone's in my class, there's a good chance we may wind up working something out. It may be because of a problem. It may be that you got sick and went to the hospital, and now we've got to work something out so that you can get your work done. And by the way, we're very flexible in the CS department in supporting those things. It may just be that you found the material interesting and exciting. So you stop by office hours, not because there's a problem, but because you're excited, or we talked after class or in the hall. The other thing that's a really exciting opportunity where a lot of the students get to know the professors particularly well is we have we have I'll say very large teams, but it depends on the size of the course, of undergraduate TA teams, teaching assistant teams. So when you take a course from me, such as the course that we're talking about here, I'm going to stop the share here just because it's sort of tying up the screen. When you take a course from me, I'm around quite a bit and I'll help you with your work. But for a course like CS40, I think we had 35 undergraduates working as our teaching assistants. So they're available 8 or 10 hours a day that you can go see them in the lab and ask them to help you with your problems. Those teaching assistants work pretty closely with the professors. And in fact, we've instituted a program of what we call teaching fellows, which is after you've been a teaching assistant for a while, if you're really good, we invite a few each year to be our teaching fellows, which are undergrads like you, who become our partners in teaching the course. So at this point, for example, when I have 35 um, teaching assistants, I mostly don't schedule them myself. I mostly don't decide who's teaching what, although I'm available and happy to help. We let our undergraduates run the teams themselves. And those teaching fellows work with us very, very closely. We see them all the time, almost every day. We interact with them on Slack every few hours. So there are lots of opportunities where people get to know their professors well, chat with professors they're not taking courses from. And in general, I think Tufts has, I think my son found not just the professors, but the students are very supportive. You know, most schools, the students are nice, but there certainly are some where there's a competitive aspect. Hey, maybe I don't want to help you because you're going to get an A, and maybe I'm not, so I don't want to help you. I see very little of that at Tufts. The students are very close to each other. They team up in taking these courses. They hang out together, and it's a really nice community. And if you come visit, check in with us. We may be able to find groups of students for you to hang out with, and you can ask them what the experience is like. Anything else? You're very welcome. I think it sounds like we're all done. Is that right?
Looks like it. We've only
They're,
got a
they're
few people kind of left in the room, so
right. I mean,
yeah.
if anybody wants to have another question, speak up now. And if not, I think we're going to thank you and wrap up.
Alrighty. Yeah. Thank
Okay.
you all for attending. Thanks, Professor Mendelsohn. Have a good night, everybody.
Good night.